it is this one that you see at the center of the image to the left. If you see, it's a Pickering crater with smooth plains within it. So with that dark material that you see there, it has a diameter of 180 kilometers, so it's quite big crater, and its age is around 3.5 giga-year. Here you see the periods of the moon, the pre-Nectarian, Nectarian, Imbrian, Eratosthenes, and Copernican periods, with the different absolute age that separate the different stratigraphic planes, these different periods. The periods are named after big impacts that has been happened during the evolution of the moon. In the case of Copernicus, it's not big basin in that case, and but it has very important ray ejectors that are useful for stratigraphic correlations. So since they cover a big part of the moon, they can be used as a reference. So everything and the same is done for Eratosthenes. So even for Eratosthenes, we have no big basin, but still a crater with its ejector. Imbrian and Nectarian are indeed the big basins. The Imbrian age, where Tsikowski crater formed, it's the one that is related, or at least the first part of the Imbrian age is thought to be related to the period of late heavy bombardment. The effect that Harry yesterday has explained, and which is a little bit debated and critical, because we don't know actually if this age 3.8 of the late heavy bombardment is related or not to this big late heavy bombardment event. So this important family of impactors that hit the moon at that time, because we can have effects of difficult age determination from the sample retrieved by the Apollo missions. In any case, our crater is a little bit later, 3.5 giga-year more or less, but I don't know exactly. You will discover it in the advanced course, the real age, because you will learn the method for discovering the age of this basin. More or less should be around 3.5, but you can discover something different during the advanced course. So I said that the crater is a complex Pickering, complex crater, sorry. And you see to the right the different phase of the genesis of an impact crater. So at the beginning, you have a content compression stage. During this stage, you have the formation of compressional waves and the rarefaction waves. When the rarefaction waves follow the compressional wave. When the rarefaction wave are rebounded inside the impactor due to the high temperature, and even due to the lower pressure of the rarefaction waves, you can have the sublimation of most of the impactor, as you see in the end of a content compression stage, so the second figure there. Afterwards, you have a displacement of the target outward and downward that forms the transient cavity of the crater itself. In that moment, you have even the ejecta curtain that forms. You see it in the third picture of the scheme. If the impactor is quite small, so we have, I would say more or less 20 kilometers, we have a simple crater. So the crater that is kind of shape with a concave simple shape, and with ejecta within it, fractures all around the base of the crater, and ejecta blanket even outside it. When the crater is bigger, you have a complex crater. The complex crater means that you have a rebound at the base of the crater that form a peak that you see in Tsikowski here, which is actually big complex crater because it's 180 kilometers. And then you have an effect of collapsing of the rim. So the margin of the crater are called rims. So this margin collapse within the floor of the crater, if you want, forming kind of normal faults or sliding planes, and forming kind of walls and terraces that you see in the last picture of the image to the right. In particular, here in the image that you see to the left, you see very well the rim border, and along the rim border you see the walls and some terraces that are due to this effect. Within the crater itself, they may form volcanic emplacements, or they can form even impact melts. So we may have melted the layer, as you see in the last picture to the right, or you can have even emplacement of volcanic material that come from deeper parts. Indeed, when you have an impact, you have the formation of fractures, so the opening, and into this fracture is possible that melts rise, reaching the surface. We may say that for big basins, we may have rarefaction waves that decrease the pressure within the mantle and could ease partial melting of the mantle. But this is still a debated problem, and Harry has explained it yesterday. So we are going to study this and map this crater, this image, and we will use a given data set. The data set that we will use was explained already by Ricardo yesterday. And you see to the left the panchromatic image that we will use. I would say the black and white image that we will use. It's a wide unknown camera image. It's not big resolution, but it's first time that we do a map, an image, so it's enough for us. It's 100 meter per pixels. The other image to the right, it's a Clementine coloration mosaics. So these mosaics is in color, as you see, and these color are obtained thanks to band ratios. What it means, you take images that have been taken in a given wavelength range of the spectrum. So we have, in this case, for the red, for example, we have a 750 nanometer at the numerator, and it's divided by the image that has been obtained at the wavelength of 540 nanometer. So this ratio gives us some information. In particular, we have red regions when we have low titanium or high glass content. When we have more greenish region with a different ratio, we have iron on the surface and possible mafic minerals. We know that within these basins, we may have the emplacement of volcanic material. The volcanic material are made up on the moon mainly by basalts. And basalts are rocks made up of two important minerals that are pyroxenes and olivines. Both these minerals are rich on iron and magnesium. Just to recall you what olivine is, are that beautiful greenish crystals that you may find in some basaltic island, volcanic island, even on Earth. There are beautiful examples in Hawaii and also in Lanzarote. And they come from deep into the mantle of a given body. So you have this kind of basalts made of pyroxene or olivine. So that's why inside Sikorsky crater, here you see this greenish, yellowish material. Then we have the blue channel that say us the content of titanium. So if we have high titanium, we have more blue material. Or even if we have lunar surface maturity. So you have to consider when you see these color features that nothing is almost red, or almost green, or almost blue, but you have the in-between color, so that the red and green give you yellow, and the blue and red give you magenta, and green and blue give you the cyan color. So you can understand in a way a little bit the composition of this material just looking to the colors of this image, and you can compare it with the morphologies that you see on the left image. However, the morphologies can be constrained and understood even using DTMs, the digital elevation models or digital terrain models. These digital terrain models are images on which each pixel is defined by its position, obviously, and by the elevation. So to the left, you see a digital elevation model in color, in which you have the reddish color that are the lower parts. So we know that Sikorsky crater is in a lower flat area. And the blue part are the parts that are higher. To the right, you can make, using DTMs, hill shades. The DTMs that we are using is 60 meters per pixel and are derived from LoLa acquisition and Kaguya telluric camera acquisition. LoLa is a laser altimeter and Kaguya is a terrain camera. So it means that they have used stereographic projection and photogrammetric analysis for obtaining these DTMs, plus the measurement of the laser altimeter. The camera gives us details, the laser altimeter gives us precision in the determination of the elevation. The vertical accuracy of these DTMs is very high indeed. So 4 meters of accuracy for the elevation. As I said, we can make from this DTM some hill shades, so we can process the image and lightening the morphology that we have with a given source of light. So in this case, we have the sun that is coming, if you want, from the northwest to the southeast, So we have all the northwest facing slopes that are brighter and the southeast facing slope that are darker. And this gives us the possibility to understand better the morphologies of the units and assisted by instructor afterwards for these units, for the recognition of these units, and mainly for the determination of the contacts among these units, because this is really the difficult part, even the distinction of the unit itself. So you don't have to recognize all the units that I will explain here, and or I would say you have to recognize them, but you don't have to map them. You may map some of them according to the instructors, I would say, needs and suggestions. So you see that each unit has its own symbol and acronym. So I call it we can find the Zykowski ejecta. The Zykowski ejecta can be visible here from these chains of small craters. The margins and the RTAJ, the margins are not very well defined, so are approximate, but you can find them from the surrounding regions just because of these, I would say, red crater chains and ejecta materials. Then you have the crater rim, Zykowski crater rim, TSR, which is the material which is making up the rim itself. Okay, so it's very, very, very proximal ejecta material. Then and even then you have the smooth planes inside the Zykowski, the dark ones, are clearly visible. And all around the Zykowski crater, you may have heavily cratered terrains that are the islands, the bright ones that we have seen before. If we go more in detail within the crater itself, we see that we have the central peak easily to map. It's quite easy to distinguish. Then we have the smooth plains all around. Then we have this material here, which is knobby, and it's called hammocky material, and it's due to the ejecta blanket that fall down again together with melts, fall down again within the crater after during I would say the excavation and modification stages. In particular, during the modification stages, you have the formation, as I said before, of wall and terraces. And you see wall and terraces here on the northwest, so in the up left corner. And this is the inner slope. So the inner slope of the complex crater is characterized by these terraces and walls. The walls in this case are quite well visible because are a little bit darker, and the terraces are brighter because the sun is coming from the west-northwest. I would say from the west, more or less. You have a kind of stitch here, so we have kind of different illumination between the two images that form this part of the image. Sorry, I have to stop a little bit for problem on the battery. Okay, then we can go outside the crater itself, and we see we have many other units. I would suggest you to start from within the crater, and afterward, if you have time, you can map up outside the crater. You still see the central peak to the right, lower right of the image, then the smooth plains, the black ones, and the crater's inner slope. Then you see something that is called LS there, which is a landslide that is formed during the modification stage. And you see it because you see these kind of morphologies with these ridges, okay, and the front. Further to the west, so to the left, you see craters with their own crater rim material, their own crater floor, in some cases their own central peak. This is a kind of central peak, for example, which is around, for this crater, of around 50 kilometers, a little bit more. And then you may have even deformational effects that can be happened after the crater formation, and they are really landslides within the crater. In this case, you may find it in the simple crater that you see here to the right. So you see here again a kind of two craters that are not so far from one to each other from diameters. One is more similar to simple craters, the other one is for sure a complex crater with a peak inside it. Then we see again here some smooth plains with more craters, and I will left you discovering, and your instructor discovering, why we have this kind of smooth plains and this ridge to the left. Within the floor itself, but there are many other features that can be seen on that image. Within the floor, we can use, if we want, the Clementine data to make some subdivision of the smooth plains inside the floor of Sikorsky crater. And in particular, here you see that there are more reddish and more magenta units within the smooth plains. So we have these reddish, yellowish, and magenta units within the smooth plains. So you may do even further distinctions. So after having said this part of the presentation, we can go and start mapping, and in particular, how moon data interpretation practical will work. So you will have this map on QGIS that we have seen yesterday with Alessandro. And we can see to the left, you have the project already done. So to the left, you have the vector layers, the materials that are used for maps. So the contacts and the points. The polygon will arrive afterwards. When you close your contacts, you have defined your units with the points, you can go with MAPI and form the polygons, as it was shown yesterday by Alessandro and Riccardo. Then you have the base data, the data sets that you see here on the raster images here. So we see the WAC, wide angle camera images, the Clementine data, and the digital elevation model, and the digital elevation model with the hill shades. So you will be subdivided into different groups and rooms. You should have already received the room, the link of the room in which you will be. On that room, you will find your instructor for today morning. and you will open with him the project, and you can revise better than this introduction the area with him. So the instructor will interact with you to recognize and define contacts among geological units, and also will help you in trace linear feature and contacts. If you have troubles, there will be the instructor. If you have big troubles on the technical part, we can call for expert for QGIS for helping us. Instructors are all very well trained on moon geological mapping, so they are expert of the sector. They have already done their own geological map on the surface. They come mainly from Munster, which are the place where moon is studied more in Europe, and a couple, me and Gloria from Padua. So after you have closed your polygons and you have done your map, you will also see, if you have time, even other possibility with QGIS. But after a while, so at 12:45 maximum, we should reconvene here in the main room to discuss what we have seen and the different events. So, as I said, a geological map is not saying us only which are the morphology, which could be the composition of the different things, but also, and most importantly, they can also say us about the evolution of the area. So which kind of events formed that area and in which sequence through time. So the geological evolution. So we will talk a little bit of that. You surely will talk about it with your instructors, but we can just reconvene and make a close of the exercise. I would ask you that the final products that you will have obtained at the end of this practical activity, I am going to ask you if you can send me the final products, just a screen capture. I don't need anything more. I don't need the project. I don't need the shape file, but the screen capture of what we have done at the end of the morning. It's not important to have done everything. I just want to see that you have done something and you have managed to do something. In particular, you can place your products on a folder and on the way that will be communicated to you by the organizers. And in order to have a certificate of attendance for this practical activity, I need these products. So now I want to record the certificate of attendance. I would say that all the people that have been registered will have their certificate of attendance of the lectures of the school, the general ones. But for the practical activity, at least for my practical activity, I need some products to be verified. We are not going to give score, obviously. We just want to see if something has been done. So I think I have finished this introduction. So I will leave all the participants to reach their rooms.
Matteo?
But if you have questions, please ask now, even within the chat.